In this video, we're going to take a look at a sample problem that is looking at solving uh, the wall force and the reaction force from the ground from a ladder. So this will be similar to the one that you'll make and have the elements that you'll need. So we have the man on the ladder, in this case here, and you have all the information up there. So we'll first need to draw all the forces with the force of gravity of the ladder, force of gravity of the man, from the center of mass of the man. And we have the wall force like we saw in our lab. We also have the normal force, the ground pushing up. And we also have the friction force. Without friction force, this ladder would fall. And all of these are balanced out, so are some of the forces in the y equals mass times acceleration in the y. Some of the forces in the x equals mass times acceleration in the x. And then we have our sum of the torques equals 0. So we know that the forces, there's no acceleration in the x, no acceleration in the y. And yeah, so now we're good to go to be able to figure out what the wall force is and then the reaction force from the ground. So in the x, we have the positive force of friction plus the negative wall force. Those are the only two forces in the x. In the y, positive normal force plus the negative force of gravity of the man plus the negative force of gravity of the ladder. This equals 0. And then the torques, what we'll want to do is choose a hinge point. So our hinge point here will be at the base of the ladder. And so let's look at the first force here. The force of gravity of the ladder itself would cause a clockwise rotation if that was the only force and this was the hinge. So that's a negative torque by the ladder plus the force of gravity of the man would also be a clockwise torque. So the negative torque from the man. And then the wall will cause a counterclockwise torque on the lever arm, and so that's really positive torque of the wall. And again, these are all equaling out to 0. So as we're trying to figure out what's going on with the wall, we can look at these torques, and what we're going to do is break down each of these into their own triangle here. So we need this length for the force of gravity, which is acting here. So in the previous video, we looked at how we need this length. We already know what the force of gravity is, mass times 9.8. And so we can set up a small triangle there. And we have our angle right here. And we know that we're looking for the adjacent side. And this is the force of gravity, which is half the way up the ladder. This is the ladder length. So halfway up the ladder is 2.973 meters. We know the angle, and so we can use cosine. It's adjacent over hypotenuse. So cosine of 70.346 equals the adjacent divided by 2.973. So this length here, the adjacent side, is 1 meter in length. And so we're going to place that into the first torque, so negative torque, force of gravity of the ladder times 1 meter, plus we need the torque of the man. So that length, I'll go ahead and show here. We need how far this is, because the force of gravity of the man is acting upon this portion of the ladder, perpendicular portion. So force of gravity, and again negative, don't drive the negative force of gravity of the man times that length. And when we set up that triangle, we know how far up the ladder, so this is the hypotenuse. And we're looking for, again, for the adjacent side. And that length will come out to be 1.6 meters. And then the wall, the last one we need is this length. So as we looked at in the last video, this is the length that we'll use here. This being a right angle, so we know the angle theta here, and we know the hypotenuse is 5.946. So we can use sine theta for that. So sine equals opposite over the hypotenuse. So sine of 70.346 times the length of the ladder, and that will give us force of the wall times the height, which is 5.6 meters. And we know the force of gravity is mass times 9.8, so we have the mass of the ladder, mass times 9.8 of the man, and our only unknown is all equals 0. The only unknown is the force of the wall. And when you calculate that out, the wall force will come out to be 244.65 newtons. So now we'll go ahead and take a look at how this connects to what's happening on the ground. And so we know the wall force now, and so we can take this down here to our problem in the X. So our wall force we have, and we're looking for friction. That's one part of the ground force, the reaction force that we need. And so it's equal and opposite, right? You place this in here, you can add the force of the wall the other side. So the amount of friction is also 244.65 newtons. Okay, so we're almost ready to get the full picture. Now we need the normal force. So we'll come over here to the forces in the Y. The force of gravity of the man. Again, the man, 78 kilograms, so 78 times 9.8. The ladder, 15 times 9.8. So the normal force will come out to be 911.4 newtons. And so if we look at that, we have these two forces on the ground. We have the friction force going to the right. We have the normal force. So we need to figure out what the combination of those are, and that's the reaction force, the total reaction force from the ground. And so we're going to set up a new coordinate axis. And we'll go ahead and establish our forces here. So we have the force of friction going to the right at 244.65 newtons. And then the normal force, remember tail to tip method when we're adding forces, the normal force is 911.4 newtons. So our resultant will be from here to here, angle theta. So 244.65 squared plus 911.4 squared equals c squared. And our hypotenuse comes out to be, put the final answer in another color. The final answer will be 943.66 newtons at 74.974 degrees above x-axis. So the combination of that force looks something, it's a pretty high angle, just above the ladder, 74 degrees. So this is the combination of the two. So this is what the ground has to do to keep this in static equilibrium. Then we have the wall force over here at the top, keeping the situation balanced as well there.